Now section 1.3, mathematical induction. Please take a look at example 1. Example 1 says the following. If we consider the sum of all consecutive odd numbers starting from 1, the result is a perfect square. How do we prove it? First of all, we can check that this is true for some integer n greater or equal to 1. For example, if n is equal to 1, the left-hand side is 1. The right-hand side is 1 square. 1 is equal to 1 square. Correct. If n is equal to 2, the left-hand side is 1 plus 3, which is 4, which is equal to 2 square. If n is equal to 3, the left-hand side is 1 plus 3 plus 5, which is 9. 9 is equal to 3 square, and so on. Note that in order to prove this identity for any integer n greater or equal to 1, it is absolutely not enough to check it for a bunch of integer values of n, because it's quite possible that this identity is true for n is equal to 1, 2, 3, 4, 5, 6, 7, and so on, but say is not true for n is equal to 2020. Here we want to prove that no matter what is n, if n is an integer number greater or equal to 1, the left-hand side is equal to the right-hand side. How do we prove it? One way to prove it is to use mathematical induction. Here is what mathematical induction all about. Step 1, check this for the lowest possible n. In our case, our lowest possible n is 1. As we discussed, for n is equal to 1, this is true because if n is equal to 1, a left-hand side becomes 1, or right-hand side becomes 1 square. Indeed, 1 is equal to 1 square. Step 2, suppose this is true for some integer n is equal to k, where k is greater or equal to 1. That is, suppose 1 plus 3 plus 5 plus and so on plus 2k minus 1 is equal to k squared. Of course, one can say, wait a second, what is written here is fundamentally same thing as this. We just replace n by k. How can we suppose that this is true? We have to prove it. Well, guys, there is a big difference between this and this. Please compare two words. Over here, we want to prove this for any integer. In step 2, suppose this is true for some. So the difference between this and this is the following. Instead of any, we put some. Here is why this matters. Question: can we indeed suppose that this is true for some? The answer is yes, thanks to step 1. In step 1, we indeed showed that this is true for some n. In particular, for n is equal to 1. In other words, thanks to step 1, in step 2, we indeed indeed can suppose that this is true for some integer n is equal to k, where k is greater or equal to 1. For example, for k is equal to 1. Now, step 3. In step 3, we want to prove, and now we want to prove that this is true for n is equal to k plus 1. Please compare this and this. Here there is no question mark. We just put equal sign, which means suppose this is true for some n is equal to k. Here we put question mark. We have to prove that this is equal to this. It is easy to come up with the right-hand side. We just replace n by k plus 1. But take a look at the left-hand side. If n is equal to k, over here the last term is 2k minus 1. We just replace n by k. But if n is equal to k plus 1, if we replace n by k plus 1, we will get 2 times k plus 1, which is, after we expand parentheses, 2k plus 2. But 2k plus 2 minus 1 is indeed 2k plus 1. And we will see it in a moment. In addition to the last term, it is convenient to write down the previous term. Since the last term is 2k plus 1, the previous term is 2k plus 1 minus 2, which is 2k minus 1. I said minus 2 because we are talking about only odd numbers. The difference between any two consecutive odd numbers is 2. So let me repeat once again. In order to come up with this, we replace n by k plus 1. Since we are talking here about odd numbers only, the previous term will be 2k plus 1 minus 2, which is 2k minus 1. Lastly, how do we prove this? We will use step 2. For convenience, let me copy this expression over here. Observe that by step 2, this, without the last term, is equal to k squared. So I'll replace this by k squared, done. Leave the last term without change. And now, by college algebra, k squared plus 2k plus 1 is indeed k plus 1 squared. The whole thing is proven. Guys, any questions?
So basically, is the reasoning such that we suppose that this is true for some k, and we know that it's true for some integers, and then we showed that if you were to increment k by 1 an indefinite number of times, it would remain true, and therefore it's true for any integer?
Absolutely. This is basically the idea. Since we know that this is true for n is equal to 1, and since we know how to jump from case n is equal to k to case n is equal to k plus 1, in other words, thanks to the combination of step 2 and step 3, we are able to jump from n is equal to 1 to n is equal to 2. And for the same reason, we are able to jump from n is equal to 2 to n is equal to 3, from n is equal to 3 to n is equal to 4, and so on. because the jump from n is equal to k to n is equal to k plus 1 works for any n is equal to k where k is greater or equal to 1. Is this what you were talking about?
Yes, absolutely.
Guys, any questions here? Think about questions.
When we use this inductive step, is our goal usually to make the right-hand side of the equation be in the same form with the k plus 1 instead of a k? Because we're trying to prove that it would be true for k plus 1. Our end result was showing that k squared, like having it in the form of like the k squared, but instead of it being k squared, it was k plus 1. Given a different equation, do we usually try to make it, like we try to make it be in the same form, but instead of being a k, it would be the k plus 1?
If I understand your question correctly, we are not trying to make it of the same form. Please compare this and this. Right-hand sides are different. Left-hand sides are different. We are trying to prove that in step 3, a left-hand side is equal to right-hand side using step 2.
Okay, yes, I see.
Okay, let us continue. We want to prove this. Step 1, let us show that this is true for the lowest possible n. Since n is greater or equal to 1, lowest possible n is 1. If n is equal to 1, left-hand side is 1. Right-hand side is 1 times 1 plus 1 over 2. Obviously, 1 times 1 plus 1 over 2 is indeed equal to 1. Step 2. Suppose this is true for some integer n is equal to k, where k is greater or equal to 1. That is this. So once again, it's easy to come up with this expression. We just replace n by k here, here, and here. Done. Step 3, we prove that this is true for n is equal to k plus 1. If n is equal to k plus 1, this becomes k plus 1. This becomes k plus 1 plus 1, which is k plus 2. On the left-hand side, the last term is k plus 1. And it is convenient for us, in addition to the last term, to write down the previous term. Now the previous term is k, because on the left-hand side, we have the sum of all consecutive integers. Last remark, here we put question mark. This is given. We are supposed to prove this. So, how do we prove this? As before, we will use step 2. First, let us copy the left-hand side. It's over here. And now, by step 2, the sum of these terms, which is over here, is equal to k times k plus 1 over 2. We leave the last term without change. So, by step 2, the left-hand side is equal to this. The goal is to prove that what is written here is equal to the desired right-hand side. Therefore, still we put here question mark. Please compare step 3 in example 2 and step 3 in example 1. In example 1, it's pretty obvious that k squared plus 2k plus 1 is equal to k plus 1 squared. College algebra identity. Over here, it's not immediately clear. why this, which is the left-hand side, is equal to this, which is the right-hand side. So, how do we prove that this is indeed equal to this? First of all, observation number one. Since we should prove it, precisely speaking, we cannot deduce anything from this yet, because, strictly speaking, we do not know yet if this is true at all. However, it is very convenient for us to use this in order to do manipulations. Therefore, here's a trick that we apply. Let us copy this over here. Let us do algebraic manipulations in order to come up with this. What is written here is true. And then we switch arrows. This implies this. This implies this. Since this is true, and we are done. Repeat once again. In order to prove this, we copy it over here. We multiply a left-hand side and right-hand side by 2 in order to get rid of the denominators. Done. We expand parentheses over here. Done. Over here. Done. And over here. Done. Obviously, since k plus 2k is equal to 3k, this is true. And then we switch the arrows. This, by college algebra, implies this. This implies this. So this is true. And now we are done. Folks, any questions here?
So essentially, in basic terms, we want to prove that step 2 plus the next term is equal to the formula with k plus 1. Is that correct?
Well, in simple words, when we prove the identity in step 3, we extract step 2 expression from step 3 expression. Because the whole idea is to use step 2 in order to prove step 3.
Yeah, that's what I meant.
Please take a look at example 3. Prove this. Again, n is greater or equal to 1. Step 1. Check this for the lowest possible n. For n is equal to 1. If n is equal to 1, on the left-hand side, we'll have only one term, 1 square. If n is equal to 1, the right-hand side becomes 1 times 1 plus 1 times 2 times 1 plus 1 over 6. This is 1, this is 2, this is 3. 1 times 2 times 3 is 6. 6 divided by 6 is indeed 1. Step 2. Suppose this is true for sum. Once again, this is a big fundamental difference between this and this. Here for any, here for sum. Suppose this is true for some integer n is equal to k, where k is greater or equal to 1, namely this. Step 3, prove that this is true for n is equal to k plus 1. If n is equal to k plus 1, on the left-hand side, we have the sum of the following terms. 1 square plus 2 square plus and so on plus k square plus k plus 1 squared. The right-hand side becomes, instead of n, we have k plus 1, done. Instead of n plus 1, we have k plus 2, because if we replace n by k plus 1, we'll get k plus 1 plus 1, which is k plus 2. Lastly, if you replace n by k plus 1 here, we'll get 2 times k plus 1, which is 2k plus 2 plus 1. 2k plus 2 plus 1 is 2k plus 3. We want to prove this. How do we prove it? Copy the left-hand side here. Note that by step 2, this, which is over here, is equal to this. So I'll replace this by this plus the last term. Done. So once again, what we see over here is the left-hand side. We want to prove that the left-hand side is equal to the right-hand side. So we still put question mark here because it's absolutely not obvious that this is identically equal to this. Question mark here. In order to prove it, we copy it here. Then we multiply the left-hand side and the right-hand side by 6 in order to get rid of the denominators. Done. Then we expand parentheses over here. K times k plus 1 is k squared plus k. We expand parentheses here. K plus 1 times k plus 2 is k squared plus 3k plus 2. Then we expand parentheses here, done, here, done, and here, done. Finally, we collect like terms. It's totally obvious that the left-hand side is equal to the right-hand side. Therefore, question mark is gone here. Lastly, we switch the arrows. This implies this. This implies this. This implies this. And the desired identity is proven. Example 4. Note that for the first time, n is greater or equal to 2, not 1. Therefore, in step 1, we show that this is true for the lowest possible n, which is 2. If n is equal to 2, the left-hand side becomes just 1 minus 1/2. The right-hand side is 1/2. Of course, 1 minus 1/2 is equal to 1/2. Step 1 is done. Step 2. Suppose asterisk is true for some integer n is equal to k, where, and again, here's a difference between this example and all previous examples. In all previous examples over here, we put n is equal to k, which is greater or equal to 1. But since we want to prove this for n greater or equal to 2, here we put 2. So suppose asterisk is true for some integer n is equal to k, which is greater or equal to 2. Namely, suppose this. We want to prove that asterisk is true for n is equal to k plus 1. If n is equal to k plus 1, the last term becomes 1 minus 1 over k plus 1. And for convenience, in order to use step 2 to prove this, it is convenient to write down the previous term, which is 1 minus 1 over k. the right-hand side becomes 1 over k plus 1. Again, we put here question mark. In step 2, we do not put question mark. We assume that this is true. Here we put question mark. We want to prove it. How do we prove it? Copy the left-hand side. Done. By step 2, the product of these terms, or which is over here, is equal to 1 over k. So we replace this by 1 over k. We leave this term without change. So what we see in front of us here is the whole left-hand side. But left-hand side should be equal to the right-hand side. So we still put here question mark and copy the right-hand side. We want to prove that this is identically equal to this. Basically, we can prove it in a bunch of different ways. Here I give you 2 approaches. So copy this, it's over here. Observe that 1 can be rewritten as k plus 1 over k plus 1. Now we have the common denominator. We subtract tops. Done. K plus 1 minus 1 is k. We rewrite the product of these 2 fractions as a single fraction, and now question mark is gone, because obviously after the cancellation of k, the left-hand side becomes the right-hand side. But once again, here is what is important. After you apply all these steps, put arrows that point upwards. This does not imply this, because we want to prove it. To the contrast, since this is obvious, by college algebra, this implies this, this implies this, this implies this, and this implies this. The desired identity is proven. Again, at home, you can take a look at approach 2. This is basically similar thing, just a slight modification of approach 1. Folks, any questions here?
I have a question. It's not really about the specific problem, but when would you suggest that the best method for proving something would be induction?
Excellent question. First of all, I cannot give you recommendations that always work. Here is why. Please take a look at the problem that we just discussed. This inequality. It looks like a standard problem about mathematical induction, because we want to prove it for any integer n. However, if you apply step 1, step 2, step 3 here, you will get stuck. And the reason for that is the following. The right-hand side does not depend on n. In order to apply here math induction, you'll have to modify the right-hand side first and then apply math induction. But in general, the recommendation that almost always works is the following. If you have an identity or an inequality or a problem about divisibility that involves integers, good candidate is mathematical induction. Math induction cannot be applied if you want to prove something for any real number. But if we have integers, math induction is a good approach. Did I answer your question?
Yes, thank you so much.